My name is Arianna, and today I'll be presenting my capstone to you about how roller coasters work and how technology has impacted them. Before we even begin with how roller coasters work, we need to learn a little about the history behind them. In the 16th to 1700s, people enjoyed attractions called Russian ice slides. Now I know what you're thinking. Oh my goodness, roller coasters existed back then! Technically, these weren't really roller coasters. These were basically sculpted blocks of ice that people would slide down. This was the main type of roller coaster, even though it wasn't, until 1885, when Marcus Adler Thompson created the Switchback Railway in Coney Island, located in Brooklyn. This was the start of the roller coaster golden age, when people started building roller coasters all over the place. The next milestone in roller coaster history was Matterhorn bobsleds, the first steel roller coaster located in Disneyland, California. After this, people also started building steel coasters like crazy too. Yet again, there was another milestone in roller coaster history that took place in 1978. The first electromagnetic roller coaster, called Montezuma's Revenge, was built. But what even are electromagnets? Electromagnets are special coils that are wrapped around the conductor of electricity, usually a nail or a screw, because coils fit better on a long and skinny cylinder than a fat and short one, for example a penny, and then connected to a battery with the rest of the coil. One side connected to the plus side, the other connected to the minus side. The electricity passes through and causes the coil and the nail or screw to have a north and south side because it creates a magnetic field, like all magnets do. You probably picked up on this already, but I'm going to say it anyway. This means the coil becomes magnetic. Of course, you can't use any old house magnets like this one to power an entire roller coaster. Electromagnets have two uses on a roller coaster, one of which is the brake. Eddy current brakes, which is the name of electromagnetic brakes, work by having a magnetic connection between the car and the track. The operator reverses the current, so the car and the track are attracted to each other, creating a braking force with the help of friction. Electromagnets can also be used to accelerate the car up the first hill instead of using a chain. But how is that even possible? That's the complete opposite of what I said less than 5 seconds ago. It's actually not that different. The operator does the same thing to brake, but instead of turning the current so the car and the track are attracted to each other, he or she reverses it so they repel. Therefore, it will burst forward. But if chains are used more often than electromagnets, are chains better? Well, electromagnets are safer than a chain because the attraction between the car and the track is a lot stronger than a chain, so the chances of it derailing is lower. Not only are electromagnets safer, but they're more efficient. Instead of having a chain drag you up the hill, building more potential energy like this, which takes a really long time, you can stock up a good amount of kinetic energy and burst up the hill. Electromagnets are also better brakes because friction brakes need to be replaced more often due to metal wearing off, which will lead to a bigger cost. So, electromagnets will also make you go a lot faster. Again, you can't use any old house magnets to propel an entire roller coaster. So I guess you could say electromagnets are a little better. Electromagnets have been a big advancement in technology that has impacted roller coasters. But how has other technology impacted them too? Technology has impacted roller coasters in many ways. It affects the safety, efficiency, and amount of time it takes to design one. There are special roller coaster designing softwares that you can use to build your roller coaster. Instead of drawing it all out on a blueprint that took 3 months to draw and spill your coffee on it. These programs tell you the elevation, which is the X, Y, and Z of your roller coaster. So if your initial hill, which is the first one, is 65 meters in the air, and your second is 999,999,999 plus meters in the air, you know that there's either a problem in the cost, the physical possibility, the program, or your brain. Technology has also affected the safety because now there are improved restraints instead of a measly seatbelt. So far, we've been talking about electromagnetic roller coasters and non-electromagnetic roller coasters. But now it's time to talk about two different types of roller coasters, wooden and steel. Wooden coasters are a traditional style with steel rails and a wooden track. These coasters are a thrill after their wildness, steep drops, and more. On the other hand, these roller coasters often lack corkscrews, which are kind of like loops, but they twirl you upside down without the giant oval, overbank turns, which are turns that face the inside of the roller coaster, and loops. But steel roller coasters often contain corkscrews, overbank turns, loops, tunnels, and high speeds. In conclusion, roller coasters can work in many different ways. There is a specific way to make them physically possible, but never a right way to make them fun. And thank you for watching my presentation.